I mentioned electrochemical gradients earlier, so I want to spend a little bit more time on what that means because it's important for neurophysiology. So electrochemical gradients, I want to break down that word. There's an electrical component and a chemical component. An electrochemical gradient is referring to the combined force, so a gradient, a difference that creates a force in the combined electrical gradient and chemical gradient. It's basically saying both these components are important, both the electrical part and the chemical part. They're related, so Na plus is a chemical. It has a concentration, wherever it is, it has a concentration, but it also has a charge. So anything that is a charged molecule or charged particle has an electrical gradient, but because it also is a thing, it also has a chemical gradient. So they both need to be considered. So this nice image here is showing each of these gradients separately. So this top one here is the concentration or chemical gradient. This we saw in chapter 1, right? The difference in concentration of whatever substance we're talking about. It could be, these little red things could be sodium, glucose, some protein, whatever. And if there is more inside, in this case, there's a driving force for it to move outside. If there's more outside, there is a drive for it to move inside. Does it move in or out? If there is either a way for it to do it. So if it is a charged ion, only if there's a protein that allows it to move through that membrane. So the permeability of this also matters. So just want to separate the gradient from the permeability are two separate issues that we've already talked about. So chemical gradient exists regardless of whether something can actually move through. But there is a drive for it. Down here, this is showing the electrical gradient, and this is based in the basic idea that negative and positive attract. Negative is going to go towards positive, positive is going to go towards negative. There's an attraction there that is a driving force. So when you have all negative inside the cell, the positive is going to be attracted to it. That is an electrical driving force. So this could be whether it's sodium, potassium, whatever positive ion it is. This negative ion could be chloride, could be negative proteins, whatever, it doesn't matter. It could be different things, right? This could be K plus and some Na plus, both of them mixed together, because we're just talking about electrical gradients here. And out would be negative to positive. So the idea is that these both need to be considered. It gets pretty complicated, and in this class, we're not going to go into all of the detail on how you consider each of these in every instance. There's something called the Nernst equation that would allow you to do that for each ion that you would consider in a more advanced class. I do want you to know, though, that they're both important, and then be able to use this term electrochemical gradient, which again is considering both gradients. So one way to do this is I want to get you some practice here. Let's look at this scenario. Make myself smaller. Come on. There we go. So in this scenario, we've got an artificial membrane here. Assume it's not permeable to Na plus, because if I don't show you a protein, there's no protein there. Membrane protein. Here's this concentration of sodium outside and concentration of sodium inside. Millimolar is just a measure of concentration. And just considering this, just sodium in this scenario, is sodium going to move in, out, or not move, and why? Is there any of these gradients here? So let's walk through this. There is no chemical gradient. There's no difference in concentration. Is there an electrical gradient? Yes, it's more positive inside the cell than it is outside of the cell. What does this mean for a drive for sodium? It means sodium is positively charged. It's going to move away from that positive towards the more negative place. So the answer is going to be out, and there is an electrical gradient. Got it? Okay, let's do another one. Potassium will move which direction? Because there is a what? There is a chemical gradient. There is not an electrical gradient. Zero, remember the outside is always zero. So our potassium is going to move out. And it's going to move out down its chemical gradient. Now you also see scenarios where something will move down its electrochemical gradient. So let me actually just do one more, and I don't have this, so I'm actually going to change this now to my, oop, I want a different color. Change this to -50. In that case, we've got an electrochemical gradient. Potassium is still moving down its chemical gradient. It's also moving down its electrical gradient. In terms of when those oppose each other, that's beyond what we're going to talk about in this class. In terms of when you have opposing electrical and chemical gradients, we'll see some situations where the chemical and electrical gradients are in opposite directions, but I will just tell you which one prevails. And know in the future, there are formulas you can use to calculate those actual forces.